Among the many ways to represent probabilities, probability tables is perhaps the one that's more easy to visualize because all of the probabilities are just laid out all together in front of you, and unless the question is specifically asking for it, there's not a need to repeatedly apply these same probabilities. Let's take here this table showing the probabilities of getting a number on a biased six-sided dice. So if something says it's biased, it means that it's more likely to land one way than the other. A fair dice would be having 1/6 chance equally of each. But as we can see here, the probabilities of getting different numbers, the ones we have already, are already different to each other. We're told that 1 is rolled the same number of times as 6, and that 3 is rolled the same number of times as 5. And using just this bits of information, we would be wanting to fill in the rest of this table here, these 3 blank sections. Well, if 1 is rolled the same number of times as 6, that means there must be the same probability of getting it. So if 1 has a probability of 1 over 12, then that must be the probability for 6 as well. Now for the other two, we know that the 3 and the 5 are going to be the same as each other, just as the 1 and the 6 were. But what reference point do we have for what their fractions are? Well, the key to this here, as it will be in a number of different places in probability, is that the sum of all the probabilities in any given one scenario must add up to equal 1. 1 is a certainty. Working backwards, therefore, to fill in the gaps that we're missing, if you had 1 minus a 12th, minus a 6th, minus a 3rd, and minus that other 12th, this your calculator would give you in a simplified form as 1 over 3, 1/3. Although we're not saying that these are individually 1/3, it's 1/3 between them, and we've already established that they have equal weighting, they're the same as each other, so we'll split it exactly in half, meaning that they are in fact each a 6th. Which actually for a dice is what you'd expect them to be. They're not what's been biased, apparently. And that's pretty much the main principles behind these questions. The fact that all of these probabilities here have to add up to 1. So if you're missing any gaps, you could do 1 minus the rest. You're going to use these statements to work out the weighting between them. For instance, if this had said that 6 is twice as likely as 1, then this would have been a 2 over 12 here, or 1 over 6. And the other thing might be expectation. Let's say that we have these probabilities now, and the question says, therefore, that the dice is going to be rolled 30 times. How many times could we expect to get a 4, therefore? Well, if it's a probability of getting a 4 is 1/3, and we're going to roll 30 times, you just do the number times the probability, 30 times 1/3. Based on that, we would expect to get 4 10 times. All right? Okay. If that feels straightforward enough, let's see how you get along with a question of your own. Now, if that's all right, let's see how you get along with a question of your own. Here we have another table, this time based around the colours of marbles that can be taken out of a bag. We're going to have red marbles, blue marbles, yellow and green. And we're told there's a 0.45 chance of getting a blue marble and a 0.25 chance of getting a yellow marble. Fractions and decimals, it doesn't really matter. We can use either in these tables. Usually we're just going to be consistent though. Now in the statements we're told that there are twice as many reds as greens, and that there are 18 blues in reality, and therefore it's asking how many reds are there really. This question is actually going to be a little bit different because you may want to think of it slightly like ratios when you're getting into this bottom bit here with working out the reds. But let's see how you can get along on your own to start with. So try to work out the probabilities of the reds, and then how many there are. Pause the video, have a go on your own, and then press play when you're ready to compare. Alright, so again, these probabilities need to add up to 1. So to work out what the red and the green are together, if we'll just do 1 minus that, 1 minus the 0.45 minus the 0.25, that's going to leave us with 0.3. So 0.3 is left, and we need to split that somehow between the red and the green. Well, there's twice as many reds as greens. So that's like a ratio of 2 to 1. Well, splitting 0.3 into 2 to 1, that's going to be 0.20 and 0.10, twice as many reds as greens, and they add together to make 0.3 again. Now that we have this probability, we can compare to the numbers of blues. Reds to blues, in terms of probability, therefore, is 0.2 compared to 0.45. So in reality, the blues are 18. So how many reds are there? Well, if you want to go across ratios, take the number you currently have, divide by the number that you're on the side of, times by the number of what you want to get to. So it's going to be 18 divided by 0.45 times by 0.2. That gets you that there are 8 red marbles. All right? Okay. Let's end off then just by looking at an actual question taken from a paper. Again, we have a table based around colours. This time, though, they are colours of counters: blue, yellow, green, and red. And a counter is to be taken at random. We've got 3 of the 4 boxes filled in this time. So blue is 0.2, yellow is 0.35, and green is 0.4. Part A, work out the probability of getting a red counter. Well, yet again, this is just a matter of the fact that they all add up to 1. So if you were to do 1 minus 0.2 minus 0.35 minus 0.4, that is going to leave you with 0.05 for the reds. From this, though, for part B, said, what is the least possible number of counters in the bag? And give a reason. Well, right now, we have these expressed as decimals. These are not going to be numbers of counters. The number of counters has to be whole numbers. But we know it's in this ratio. We know that it's 0.2 to 0.35 to 0.4 to 0.05. Well, if we wanted to make these whole numbers, we could times by 100. We're going to times by 100, not just 10, because even though timesing by 10 would get this to be 2 and this to be 4, that would still be 0.5 over here, for instance. So timesing everything by 100, and you have to times everything to keep it consistent. This becomes a 5 here. This is now 40. This is 35. And this is 20. Okay, they're all in whole numbers. This would be an amount of counters that would work, that would have these probabilities. But it's not the least possible number. Now that they are in whole numbers, we need to simplify by taking out a common factor. What number goes into all of these? 5. So if you divide them all by 5, 20 becomes a 4, 35 becomes a 7, 40 becomes an 8, and the 5 becomes a 1. Once you have reached a 1 in your ratio, you cannot simplify any further, because obviously that's the smallest positive whole number. This, therefore, is the ratio, therefore the actual least possible number, if you add these up, so 4 blues, 7 yellow, 8 greens, and 1 red, you are going to get that there can be 20 counters. And as for your giving the reason, as that they has to be made up of whole numbers, yet you now have only 1 red, which is, as we say, the smallest whole number.